Hi, in this video I'll introduce the supervised learning problem. I'll do this by giving you an example. Imagine you have 3 small coins and 3 larger coins. These coins might also have a weight, and they might also have some volume. So we could draw a table where we have all these weights and volumes. So the small coins might have weight 2, 3, 2 and volume 1, 2, 3. And maybe the larger coins would have weight 5, 5, 4 and volume 4, 4, 5. Maybe let's change these so they're a bit different. 6 and 5. So we'll talk a bit about classes and classification. So let's say we'll call the small coins for class -1 and the larger coins as class +1. So I have 2 values associated with each coin, so I could now draw or represent each coin with a point in 2 dimensions. So I'll have weight as my x-axis and volume as my y-axis. So the largest values here are like 6, so let's just have 6 ticks. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So then the first coin could be represented by 1, 2, 1. And I'll just give it a minus because this is the class -1. So then 3.2 would be 1, 2, 3, 1, 2. It would be this. So then the third coin could be represented by 1, 2, 1, 2, 3, this place. And then the first of the larger coins would be 1, 2, 3, 4, 5, 1, 2, 3, 4, this point. And then this would be 6 and 5 would be this 6, 1, 2, 3, 4, 5, this point. And the final one would be 1, 2, 3, 4, 1, 2, 3, 4, 5, this point. Great. So these are the smaller coins and these are the larger coins. So if I told you I had a coin and if I drew it in this way, it would be represented at this point, you'd probably guess that this is a larger coin because its weight and volume is similar to the other larger coins. And in the same way, if I told you I have a coin and it was represented by this point, you'd probably say, well, this is probably a smaller coin. So you can imagine that between these 2 classes of coins, we have a boundary that kind of tells us it's a decision boundary. Everything above would be a larger coin and everything below would be a smaller coin. So this would be a function that, given weight and volume, would tell us which coin we're kind of representing by the weight and volume. So if we wrote this down, we would write it as a function f that has weight. It takes weight and volume, and it tells us which class the coin should belong to. So it could be a small coin, or it could be a larger coin. So this is really what we want to recover. We'll call this our unknown target function. This is the goal of our problem. We want to figure out something about this. We want to learn this thing. So a little bit about notation. We usually denote this as f is from x to y. So in this case, x is our input, and is in this particular case, our input is of the form weight and volume, and the output is the classes. So in this particular case, we would probably have that the input would be the 2-dimensional vectors with real entries R2, and the output would be well, small or large coins, but we would represent it as -1 for the smaller coin class and +1 for the larger coin class. So we want to kind of learn this function, and to do this we have our data. We have these points we already know. So in this sense, you could think of this guy as being a two-dimensional vector x1, and this guy as a two-dimensional vector x2, and so on. I'll call this x3, x4, x5, and x6. Then also for each of my vectors, I'll have a label that'll tell me which class is this point in. So I'll have like, we could think of y1 for the first guy, y2 for the next vector, y3 over here, and also for the larger coins I'll have y4, y5, and y6. So each of these would tell me which class they would be in. So these guys would be -1, they would be in the -1 class, and these guys would be in the +1 class. So you'd write I have data D, which is a set of points x1, y1. So it's a set of pairs where the x's is the points and the y's is the corresponding label. So in the general case, I would have n of these guys, where xi is an input, so, and yi is in my output, right? So in our particular case, we had n was 6. We had 6 data points, and we had that x was the vectors, the two-dimensional vectors with real entries, and y was -1 and +1. Great. So the goal is now to use this data to approximate the unknown target function. So to do this, we will define an error measure. So we'll say for each h, I can compute the error, and the error will now tell me how good am I approximating the unknown target function. So let's see if we can define the error of some h. We'll say it's the sum of i's 1 to n. So we'll sum over all the points, y is 1, y is 2, all the way up to n. So we'll sum over all the pair of points and labels. And then we'll say, well, what did my hypothesis say on this point, and what is the points value? So this is my prediction, and this is the real value. So this might be +1, and this might be +1. Then I predicted correctly. But it might also be, they might also be differently. And then I did a misprediction, and then I might have some error that I'll sum up. So the error is kind of like independent for each point, and I'll just add up how much error there is. And then you could do this in a lot of different ways. You'll have like another function that'll be a point-wise error, and you can do this in a different ways. We'll get into this later. But so you'll sum the errors on each of the points, and then you'll do like an average thing over here. Great. So this is my error, but I'm going to call this the in-sample error now, because it's the error in my data set. Okay, so